Alrighty, so welcome back everyone. Today we are going to start talking about multivariate linear regression. Um, Single variable, single parameter linear regression isn't all that useful because it's kind of rare that you have data that consists of a single parameter. Um, so we are going to expand from a single variable to two variables and then many variables. That's where we're headed. So let's go ahead and start off with that. So we were um, doing the single parameter linear regression where we were taking the square footage as our feature, and then we were translating that into an estimate for a house price, right? And so we said that theta sub zero was equal to zero. That's how we simplified our model. We had our hypothesis function was equal to just theta 1x, right? And so that's all well and good, but if you have your data and it looks something like that, when I fit a line to the data, maybe something like that, it's definitely not hitting at the origin. This is your offset, that your baseline value. So we need that theta 0 to not equal 0. That is important, um, so that we can always have the threshold for our model. And in the case of the price of houses, if the y-axis is the house price, this is the minimum price for a house. A 0 square footage house, how much would that cost? It's kind of a silly concept, but there is a bare minimum that you just don't go below for a house. So it does make sense in that respect that we would need a theta 0 not equal to 0, the y-intercept not equal to 0. So that's where we are right now. We're going to change our hypothesis function now to be h of x is equal to theta sub 0 plus theta 1x, like that. Alrighty, so if we change our hypothesis function to be this, um, we had to be a little bit careful, because now we're going to say that our theta sub 0 is equal to theta sub 0 minus alpha times, and I'm just going to call it the partial of the cost function with respect to theta sub 0. Okay, that's just like what we had before when we had theta 1 was equal to theta 1 minus alpha times the derivative of a cost function with respect to theta 1, right? So that's what we had before. And just as a reminder, we had the cost function was j was equal to 1 over 2m summation I from 1 to m. And then it was before, and I'll change this in just a second, it was theta 1 x minus, and that's xi, and that is minus yi quantity squared, right? That's our MSE. But now we're not going to have that. Now we're going to change this to include our theta 0. So it's going to be theta sub 0 plus theta 1 xi minus yi. So this is our new hypothesis function, where we now have two parameters that we can kind of work with. And we're going to say it's two parameters, even though I know it's just the offset, but we're going to go with that. Alrighty, so now that we have made these changes to our hypothesis function, we are going to have a problem with the code if we try to use the code like we've been using. So let me clear this, and I'll show you why we have a problem with this. Okay, so if I do where I have theta sub 0 gets theta sub 0, theta sub 0 new gets theta sub 0 old minus the alpha times the partial of the cost function with respect to theta sub 0. So this is in the code, and we'll assume that that means something in the code. And then theta 1 is equal to theta 1 new, it's equal to theta 1 old, minus alpha partial of j with respect to theta 1 now. Alrighty, so I run this code, and I immediately have problems. The code just blows up. It works. It doesn't error on me, but it gives me values that make absolutely no sense. And so the reason behind this problem, if I run the code as is, if I implement this theta sub 0 gets updated, then theta 1 gets updated. It all comes from this new j that I have right here. Because this new j, this cost function, includes the hypothesis function, right? And the new hypothesis function is theta sub 0 plus theta 1 x, right? That was my new hypothesis function that's in my cost function. So this new cost function has the new hypothesis that includes these two parameters. And so what happens is, if I implement the code just as is, I get theta sub 0 new gets theta sub 0 old minus alpha times that. That's fine. That executes absolutely fine. But then I get down to the theta 1 assignment. When I try to assign the theta 1 new value, it's equal to theta 1 old value minus alpha times the partial of the cost function, which includes the hypothesis, which now has, for the very first time, let me do a bright color, a brand new theta sub 0. One that just got updated from this step right here. Okay? So when I call this new theta 0 within my adjustment for theta 1, I'm going to wind up with garbage values, because my new theta sub 0 is equal to the old theta sub 0 minus this times cost function. That's fine. But now the new theta 1 is equal to the old theta 1 minus alpha times a value that has already been updated. It is not used. This is not using the same cost function as this one. This cost function includes a new theta 0. And you're definitely not going to like the results with that. So what we have to do instead is we have to be a little bit clever, and we need to not assign these two the values immediately. What we're going to do is we are going to assign the values to temp 0 and temp 1. Then, after I've done all of assuming we'll just do two parameters. Once I have run through this is the same cost function as this cost function now. Now that I've run through both of those, I update in a batch. Theta sub 0 gets temp 0, and theta 1 gets temp 1. So now that I have at the same cost function, stored the values into temp 1, I finished these calculations using the cost function. Now I change the value of theta 0 and theta 1. after I've done all the calculations. So um, I hope that that made sense. It is one of those weird things that, to be honest, if I had written the code from scratch without ever having seen any other person's code, which I did this once and it blew up on me because that is such a fine point that these two cost functions are not the same once you've updated it with the temp zero, or rather the theta zero call. Um, that is that kind of error is exactly why I like to call libraries that someone much smarter than I am has written and tested and retested. So I know that I'm not messing things up. So that said, let's go to the next slide. Alrighty. So what do we have here? Oh, yeah. So this is kind of cool. I think you're going to like this. Let me clear this and go back to my yellow. You know what? I'm not going to do yellow. Let's do green for a little bit. No reason whatsoever. Just feel like doing green now. Um, as soon as we switch from one parameter to two parameter linear regression, we no longer have just a simple parabola shape. So what we typically had was, when we did our cost function, if you remember, it was a parabola that came down like that. And this had a global minimum right at the bottom of the parabola, right? And so we had the very clever gradient descent algorithm that would work its way down. It might start with a guess here, and then the guess would go here, and then it would go here, and then here, then here. And it would finally gradually hit this minimum. But now that we have two parameters, we do not have a parabola anymore. Instead, we have, this is just theta 1. But if we have theta 0 and theta 1, we get something that is, instead of a parabola, oh boy, I'm so not an artist. That's not too bad. What we get is a bowl. Okay, this is theta 0 and theta 1, where you can imagine maybe heading up. This is our cost, but the coordinate system here and here might be theta 0 and theta 1. And so something that is quite nice at this point is that even though it is no longer a parabola, it still has a global minimum because it's a bowl. It is a bowl that behaves like a normal bowl should. Every bowl has a minimum value at the very bottom of the bowl. So I mean, it's not some crazy bowl, but it doesn't matter where I start. If I start here, if I start here, if I start here with my guess, I am still going to get down to the global minimum. Now, you may take kind of a roundabout path. It's not going to be a straight line, I can tell you from having watched the values when I was first going through multivariate linear regression, trying to understand how everything works. You'll wind up getting a little bit far down with one of your parameters, and then it'll move from that new value and try to minimize the next one, and it kind of meanders its way down, but it will eventually get down to the bottom every time. And so that property of having a global minimum that you are guaranteed to hit given enough time and the right step size is what's referred to as a convex problem. This is what you want. You want something that's convex because no matter what your initial starting conditions are, it will reach the global minimum. That is not what it looks like in many problems out there. As a matter of fact, once you go past 2 parameters, you're no longer guaranteed. But you can imagine if I had 38 features, I'm going to have tons of local minima that I can get trapped in. To kind of give you an idea of what I'm talking about, you could have something like this. Now, if I start right here, I wind up here and I think I'm done. If I start right here, I wind up down here and I'm done. Start up here though, I wind up right here and I think I'm done. So when a problem is no longer convex, your initial conditions can completely change what your results are, which is not something that you want in a robust algorithm. So with that in mind, we are super happy that the 2-parameter, at least, linear regression is still convex. So that's a good thing. Alrighty, so now let's move on to the next slide. And we can start talking about something that is a little more complicated than the 2-parameter, because honestly, the 2-parameter doesn't. Again, that's an extremely simple model that you're not going to see in the real world. So what we want is to move from 2 to many features, and I am going to show you how we can get that. So let me clear this, and I'm going to go back to yellow because yellow I think is the easiest to read out of all of them. Alrighty, so once we go beyond just the square footage, saying the price of a house, once you get more features, you need to kind of arrange things a little differently. So let's start off with, I'm going to make a little table here. So let's see, I'm going to have something like this, like that. All right, this is going to be x sub 1, and it's going to be the size of the house in square feet. X sub 2 is going to be the number of bedrooms. So number of bedrooms. Okay. And then x sub 3, we're going to call that the number of floors of the house, or stories, whichever one you prefer. Okay, and then x sub 4 is going to be the age of the house. And then y is going to be our price. And we're going to look at in thousands of dollars. I always forget to put that little dollar sign at the beginning. Alrighty, so I'm pulling some values. I won't say they're completely out of thin air, but they're sort of out of thin air. So let's see, we have 852 square feet, 2 bedrooms, 1 floor, age is 36 years old, and it's going to run 178,000. Alrighty, then 1534, 3 bedrooms, 2 floors, the age is 30, and then that one costs 315,000. 1,416 square feet, 3 bedrooms, 2 floors, 40 years old, 232,000, and last 2104, 3 bedrooms, 1 floor, 45 years old, and we're going to say that costs $460,000. Okay, so you can kind of think of each one of these as being a house that's been put up on the market. And so there we go. We need to change our notation a little bit. So first things first, n is going to equal the number of features that we have. Okay, in our case, we have 1, 2, 3, 4 features. Okay, and we're going to say that x I sub j is going to be the jth feature of training example I. Okay, so this is going to let us refer to individual elements inside this table that we have already. So right here, this is the way that we can refer to individual elements, but if we want to refer to a single training example, all we have to do then is just refer to xi. That is going to be the ith training example, and it is going to include all of the features. Okay? Now, if I had something like x3, that would be the third training example. And it would look something like (14, 16, 3, 2, and 40). Okay, so just reading across right here. Okay, now this right here is a 4 by 1 matrix or vector, whichever one you want to call it, totally fine, where 4 is the number of rows that we have, and the 1 is the number of columns. So this is row, and this is column. Okay, just like that. So let's go. Hopefully all that's good. We're about to use it. Let me go to the next slide. So kick over here. Now, we have greatly increased the number of features that we're going to be considering to figure out the price of a house. So let me close this and work on a new hypothesis function to fit this new data, this greatly expanded data. Let's see. So clear that. Alrighty. So the new hypothesis function is going to be, well, we're going to have theta sub 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. Alrighty. Now, the thetas, more than at any other point, once you start getting the number of features, it will start to make more logical sense. These thetas, specifically these thetas right here, theta 1 through theta 4, those are going to set the weights for the features. In other words, these parameters, these theta 1 through theta 4, those are how much each one of the feature values is worth. So for example, if I had, this is just completely kind of just made up, if you will, theta sub 0 plus, let's say theta 1 was found to be 0.2 x1 plus 30 x2 plus 52 x3 plus, oh, sorry, not plus, minus 2 x4. So what does this mean? Well, this 0.2 is a square footage feature. This one is the number of bedrooms. This one is the number of floors, or is it, did I get that right? Floors and bedrooms are in that order. Bedrooms and then floors, yeah. So this is number of floors right here. And this is the age of the house, okay? Now, what this says is that 0.2 thousand dollars per square footage. So $200 per square foot is how much the price of the house, what it's set by, if I said that correctly. Each bedroom is worth $30,000 in the price of the house. Each floor of the house is worth $52,000. And for every year that the house is old, you lose $2,000 worth of value. That's why these values, these parameters, those are the weights that are applied to the actual feature values, okay? So this is a completely different shift that we're going to be doing from here on. Your thetas are the weights that set the importance of the features, okay? Now, here we go. If, well, you notice right off the bat, I left a space here after this theta 0. If I want to keep this same kind of notation, I can put an x of 0 here and just let x of 0 equal to 1, okay? If that's the case, then this is still just theta 0, because multiplying theta 0 times 1 is still just theta 0. But now I can say my hypothesis function is this beautiful thing right here. Theta 0, x of 0, plus theta 1, x of 1, plus theta 2, x2, plus theta 3, x3. It flows. There's a patterning that's going on there. All right? And so that's kind of important because where we're headed next is someplace I think you're going to enjoy going to. We go to the next slide. We are heading to linear algebra land. All right. So linear algebra land, what do I mean? Well, first off, let me erase this x of 0 equals 1. So I'll have a little more room. I'll denote that up here. This is a 1. X of 0 is always going to be a 1 for us, okay? Now, the way that I can make things more compact with linear algebra is I can say, well, I've got theta is going to be theta 0, theta 1, theta 2, theta 3, and theta 4 as a column vector. Okay? I'm going to do the exact same thing with x. X is going to be x of 0, x of 1, x of 2, x of 3, x of 4, like that. Okay? Now, in order to write this hypothesis function very compactly using the linear algebra, I can have the following. Well, let me define something first. If I have a column vector, I'm going to call my column vector, let's call it J for absolutely no reason. Maybe it's J0, J1, J2. Okay? If I did the transpose of J, which is indicated by a T as kind of like an exponent, that reorders it to J0, J1, J2. Instead of a column vector, when you take the transpose, it becomes a row vector. Okay? So if I want to change theta to theta transpose, I now have theta 0, theta 1, theta 2, theta 3, and theta 4, like so. Now I can do theta transpose times x, where we're doing matrix multiplication here. What is matrix multiplication? Well, matrix multiplication is handled, let me see, where can I need a little corner somewhere. I think I can, I'm going to try to fit something right here. If I have A is equal to 1, maybe 2, and B is equal to 3 and 4, okay? If I have that and I do A, B, that is matrix multiplication, and that is done by taking the first, and in this case only, row, and then multiplying B first column, in this case only column. So you do like that, and once you have sent the first row through multiplying by every single column in the second matrix, you then move to the second row. But in our case, there's a single row, single column. So this is just going to be, the value would be 1 times 3, that's a 3, plus 2 times 4. So this would actually contain 3 plus 8. That would be the value. It actually boils down to an actual value. It's kind of cool. Now, theta transpose x is going to be something kind of cool, because this is going to be theta transpose times x. So we're going to have theta 0, theta 1, theta 2, theta 3, theta 4 times x0, x1, x2, x3, and x sub 4, which is going to equal theta 0, x0, plus theta 1, x1, plus theta 2, x2, plus theta 3x3 plus theta 4x4. I hope you're enjoying this. So, if I do the matrix multiplication of the transpose of theta, multiplying my x column vector, I wind up with theta transpose x equal to the hypothesis function that I have written up here. Except now I can write that hypothesis function in about as compact an expression as possible. Theta transpose x. And this doesn't care if there are 5 different features versus 500. Theta transpose x, well, it handles all of that behind the scenes. Go linear algebra. Alrighty, so that is the way that you can simplify these things by using some linear algebra. Our new hypothesis function, and it's going to be that way for a while, is just theta transpose x. Done. That's theta 0 x of 0 plus theta 1 x1 plus theta 2 x2, etc., etc. And since our hypothesis function is nested inside of our cost function, we are going to have our new cost function containing every single one of the features in this beautiful compact expression right here, theta transpose x. So our new cost function is going to be a little more tricky to deal with because we're going to have all of these parameters and features kind of locked within it, hidden inside this theta transpose x, but we'll get through it just fine. I hope you've enjoyed this. The next time we're going to go through, like we did with linear algebra, with the one parameter linear regression, we're going to go through the mathematics and the code next lecture. So I will see you then. Y'all have a great one. Bye-bye.